If you wanted to learn all fundamental particle physics, you would first need to know that the world we live in is governed by four forces: the strong, weak, electromagnetic, and gravitational force. We have a quantum description for three of these forces. The odd one out is gravity, for which there is no quantum theory as yet, but it is so weak that it doesn't have a significant effect at the quantum level, since the other forces overpower it. So it is generally ignored in quantum calculations, but after almost 100 years of scientific progress, we can very accurately describe the other three forces in terms of quantum field theories. These theories explain how particles like quarks and electrons interact with each other via these three forces. Each force is mediated by a force carrier, also called a mediator. The electromagnetic force is mediated by the photon, the weak force by the W and Z bosons, and the strong force by gluons. In a quantum field theory, we represent each of these mediator particles with a field. For example, the photon field mediates the electromagnetic force between electrically charged particles like electrons. Other fundamental particles of the Standard Model are also represented by their own respective fields. And these fields can interact with each other. Thus, the photon field can interact with the electron field, causing a repulsion of two electrons, for example. If we generalize this concept of force-carrying particles interacting with other particles, we can get all fundamental particle physics. We can take space-time, add a quantum field for each type of fermion, like quarks, add quantum fields for the appropriate bosons, like gluons, that mediate the force that the quark is subject to, and we can get a great representation of how it all works. These theories can be complicated, but American physicist Richard Feynman came up with an ingenious way to represent these interactions in what is now called Feynman diagrams. And even though these diagrams represent complicated mathematical equations, they can be visualized intuitively and drawn for any process using some simple rules. If you want to understand all fundamental particle physics with the help of these simple, intuitive Feynman diagrams, then Merry Christmas, because that's coming up right now. Before we review all particle physics, I'd like to take a moment to thank special offer, Magellan TV, for making this episode possible. Magellan is an ad-free documentary streaming service created by the filmmakers themselves. The documentary collections are richer and broader than about any other streaming service. You can dive deep into subjects like history, culture, science, and technology, and see many of them in 4K. I'm excited to tell you that Magellan is now offering a buy one, get one free gift card for the people in your life you want to give the gift of knowledge. If you're new, you'll get a free 1-month trial of Magellan. If you're already a member, you'll get an extra month anytime you purchase a gift card. There has never been a better time to spread the gift of knowledge. I highly recommend Magellan TV, so be sure to click the link in the description. First, let's learn to make a simple Feynman diagram. To do this, we'll start with particles, charges, forces, the Standard Model, which is like the periodic table for fundamental particles. What is important here is to understand what the different classes of particles can do. So on the left, the 12 fermions are represented with straight lines with arrows in Feynman diagrams. The arrow is important, just like how in an electrical circuit, the current flows through the circuit. The arrows represent the flow of fermions. No two arrows point towards each other. This is to conserve the fermion current, or in other words, we must have the same number of fermions in the end as we started with. Note, there are some other notations which use these arrows differently. If we consider time in the x direction, then we can interpret fermion arrows going forwards in time as matter particles, and fermion arrows going backwards as antimatter particles. This is the general rule for all fermions. Now, the fermions can be divided up further in terms of charges. When I say charges, I mean the electric and color charge. If you don't know what a color charge is, please check out my previous video on QCD. All 6 quarks have color charges. All particles with color charges interact with the strong nuclear force. Thus, all quarks feel this force. The quarks also have an electric charge, so they also feel the electromagnetic force. The other class of fermions are the leptons. These can be divided into the electron, which makes up an atom, and its heavier cousins, the muon and tau particles. These all have electric charges but no color charges, so they feel the electromagnetic force but not the strong force. The last 3 leptons are the neutrinos. These do not have a color charge or an electric charge. Thus, they are not affected by the strong or electromagnetic forces, and they have very low mass, so only slightly affected by gravity. This is what makes them very difficult to detect. You might ask, hey, what about the weak force and its charge? The answer is that all fermions carry something called weak isospin. This can be thought of as as the charge of the weak force. For fermions, it can be plus 1/2 or minus 1/2. So all fermions interact with the weak force. But weak isospin can also be -1, 0, and +1. The boson has a weak isospin of -1, WPLS has +1, Higgs has 1/2, and Z boson and photons have a weak isospin of 0. Note that this Z arrow is not the same as having no isospin. Both the Z and photon interact with the weak force. Everything in the standard model has a weak isospin except gluons. So gluons do not interact with the weak force. Weak isospin is a quantum number relating to the weak force. It is a property just like electrical charge is a property of some particles. The number of the charge is just related to how they feel it. Weak isospin must also be conserved. Just like you must conserve electric charge and color charge, it is a stretch to call the weak force a force. It's more like a power. The weak force has the power to turn one particle into another particle. So, for example, it can turn a down quark into an up quark, turning a neutron into a proton by emitting a W minus boson. It is the only force that can do that. Electromagnetism and the strong force can't do this. To recap, quarks interact with all forces, electron-like particles interact with electromagnetism and the weak force, but do not interact with the strong force. Neutrinos only interact with the weak force and nothing else. Only quarks and gluons carry the strong force. Higgs bosons do not interact with photons or gluons. They confer mass to fundamental particles. So all fundamental particles with mass interact with Higgs. With that, you have the basics needed to understand Feynman diagrams. There are potentially a large number of diagrams, but we can build almost everything by looking at the most important ones where fermions interact with forces. The simplest force is electromagnetic force, described by QED, which, as we know, interacts electromagnetism with quarks and leptons. Note that the W bosons, which are the mediator particles for the weak force, are charged, so they also feel this force, but we'll ignore them for the moment. Let's interpret one of the simplest diagrams shown here. The x-axis represents time. An arrow pointing to the right represents matter particles. There are two ways this diagram can be interpreted. We can view it as an electron moving from left to right, while at the same time a photon moves from bottom to top. This would depict a photon being absorbed by an electron. This is how the electron in an atom can move from a lower orbit to a higher orbit by absorbing the energy from the photon. We can also view this as an electron moving from left to right, emitting a photon, and then continuing. In this scenario, it would represent the electron losing energy by emitting a photon. This is how an electron in an atom moves from a higher orbit to a lower orbit. By the way, this is also how a laser works. How is electromagnetic repulsion depicted in Feynman diagrams? As we discussed, the force-carrying particle for electromagnetism is the photon. This diagram, also called Muller scattering, depicts repulsion. Two electrons come near each other. An exchange of virtual photons causes a transfer of momentum, which pushes the two electrons apart. Note that we cannot measure the virtual photons, only the incoming and outgoing electrons. So sometimes this diagram is drawn like this. These both depict the same process. What about electromagnetic attraction? The diagram for this, called Baber scattering diagrams. There are two potential diagrams. The first diagram depicts an electron and positron that have opposite charges attracting each other. This also happens through the exchange of virtual photons. This looks very similar to the diagram for repulsion. The only difference is that the photon exchange in this case results in exchange of negative momentum, which attracts two particles instead of positive momentum, which repels two particles. We can see this in our boat analogy, where the boats represent electrons and the object being thrown is like the virtual photon. Positive momentum exchange is like the two people throwing basketballs at each other, which pushes the boats apart. But a negative momentum exchange is like two people throwing boomerangs, which results in the boats being attracted to each other. The second diagram shows a different phenomenon, which can also occur when electrons and positrons are near each other. This shows that when the anti-particle pair come near each other, they annihilate, resulting in energy production or photons being created. The energy of these photons, in turn, can create a new electron-positron pair. Weak force. This leads us on to the slightly more complicated weak force. This force is felt by all of the standard model particles except gluons. The most interesting weak force diagrams involve W bosons, which can have a +1 or -1 electric charge. These particles can do something very special. They can change the identity or flavor of the particle. For example, they can change an up quark into a down quark. This is so important that we probably would not exist without it. So, for example, here's one of the most important weak force interactions relevant to life. This involves a neutron decaying into a combination of a proton, electron, and antineutrino. On the left side, we have a neutron, which is composed of one up quark and two down quarks. One of the down quarks can change flavor and become an up quark. This happens due to the weak force mediator particle. When a boson is emitted, the down quark changes its flavor to an up quark. This boson then almost immediately decays into an electron, an antineutrino. Because the new particle now has two up quarks and one down quark, our original neutron is turned into a proton. Note that charge is still conserved because the emitted negative charge of the electron is balanced by the positive charge of the proton, and weak isospin is also conserved because the isospin change of +1 created when a down quark changed to an up quark is balanced by the combined -1 spin of the electron and antineutrino. If this decay did not occur, the early universe may have been awash with neutrons and atoms may never have formed. Another interesting weak force interaction involves the Z boson. It has no electric charge, just like the photon. But unlike the photon, it can mediate interactions with electrically neutral particles like the neutrino and the Higgs. So, for example, as the Feynman diagram shows, a Z boson can transfer spin or momentum between an electron and a neutrino. But in the process of doing so, it does not transfer any charge and leaves the particles otherwise unaffected. Strong force. This brings us to strong force, which is the most complicated mathematically, but since it only relates to quarks and gluons, there are fewer interactions to understand. One of the simplest diagrams is the interaction diagram. Here, a pair of quarks simply change color. This process happens all the time inside protons and neutrons, and this color charge exchange is the glue that binds the quarks together and keeps them confined to the inside of nucleons. A blue and red quark, for example, can change colors via the exchange of a gluon. So, on this diagram, we have a red quark coming from the top left. It emits a gluon with a combination red and anti-blue color charge. Gluons always have a combination of color anti-color charges. The outgoing anti-blue of the gluon immediately turns the quark into a blue quark. The blue quark at the bottom absorbs this gluon. Its blue color gets neutralized by the anti-blue contained in the gluon. And this quark turns red by absorbing the red that was also part of the gluon. Note that color is conserved in this interaction. Because gluons themselves contain color charges, they also interact with each other via complicated diagrams. These gluon-gluon interactions is what the flux tubes inside nucleons are made of. These tubes are formed when you try to pull quarks apart. As discussed in the video about QCD, the diagrams here show possible constructions. Now, let's look at what is the most complicated Feynman diagram in this video, but may very well also be the most important. This diagram represents the strong force interaction that binds protons and neutrons together in the nucleus. Without this interaction, there would be no atoms heavier than hydrogen, and life as we know it would not exist. Essentially, this diagram shows that a proton and neutron interact with each other via gluons, yielding some residual energy which becomes mesons. These mesons are a combination of quark, anti-quark pairs. These, in turn, mediate the strong force between the proton and neutron. Let's take a close look at exactly how this attractive force works. We have a proton up top and a neutron at the bottom. Keep in mind that color must always be conserved. That is, the three quarks inside proton or neutron must be a combinati of red, blue, and green, which combine to make a neutral white color. Let me clarify that this is the same way that optical colors combine, but color charge is a metaphor and has nothing to do with colors that you can see with your eyes. Inside the proton, the blue up quark interacts with the red down quark via a gluon. This turns the up quark red and the down quark blue. As this down quark leaves the proton, an anti-blue anti-quark is created together with a green down quark via a gluon interaction between the green up quark, which was initially green but turns blue the blue down quark, an anti-blue, anti-down quark, leaves the proton forming a color charge and charge neutral pi meson. The newly created green down quark remains in the proton. The pi meson now interacts with the neutron. The anti-down quark of the meson annihilates the down quark of the neutron. At the same time, there is a color exchange between the red down, blue down, and anti-blue, anti-quark, such that the quark which is not annihilated becomes red. The down quark of the meson joins the neutron by taking the place of the annihilated down quark. At the same time, an exchange of colors occurs with the green up quark of the neutron such that the up quark turns blue and the new down quark from the pi meson turns green. You might ask, why are so many color exchanges happening in this interaction? The color exchanges have to happen in order to maintain a neutral charge in both the proton and neutron. That's the way quantum chromodynamics works. It can't work without it. Note that this interaction works equally well both ways, whether you go up or down. Also note that these virtual meson interactions are what keep protons and neutrons bound together in atoms. But the attraction is much weaker than the gluon interactions that keep quarks within the nucleons, and they work only at very short distances, much smaller than the width of the proton. The last thing I want to show is how physicists produce the long sought-after Higgs boson. While there are several ways it can be made, the most prominent process used at the Large Hadron Collider is the so-called gluon fusion process. What happens is that in some high-energy proton-proton collisions at the LHC, two high-energy gluons can be produced. These can, in some cases, due to strong force interactions, turn into top quarks and fuse together via a triangle loop. This loop represents top quark, anti-top quark creation and annihilation. The energy of this annihilation can create a Higgs boson. Because the top quark has the highest mass of all elementary particles, it has the best chance to decay into a Higgs boson, which has the second highest mass of all the elementary particles. In general, when particles decay, they tend to decay into the next highest mass particle, even though there are an endless number of Feynman diagrams, if you understand the ones I just talked about, and you understand the most important diagrams responsible for the physics of our everyday lives, ignoring gravity. My message to you is that even the most...
This is what most schools are creating. A hold up the wind up robot, wind it up. Let it walk in circles, I wind it up. It follows its programming. Does exactly what it's told. Repeats the same pattern over and over. No deviation, no creativity, no thinking. A memorization machine. Put down the robot, pick up the blocks. This is what we should be creating. Hey, start building something with the block C open-ended, creative. Problem solving. Experimenting. Trying. Failing, adjusting, building something that didn't exist before. A thinker? Hey, put down the blocks, look at audience A. Right now, our education system is mass producing the robot. Children who can recite facts, who can follow procedures, who can pass standardized tests, who can do exactly what they're told. But can they think? Can they solve new problems? Can they create? Can they adapt when the situation isn't what they've been programmed for? Add a pause, most of them can't. Because they've been trained to memorize, not to think. They've been turned into machines, not developed as thinkers, of direct addressix. And if you're a parent, a teacher, or anyone who cares about the next generation, this should terrify you. Because the world doesn't need more memorization machines. We have actual machines for that. Computers that can store and retrieve information far better than any human. What the world needs, what your children need, is the ability to think, to reason, to solve problems that don't have predetermined answers, to create solutions that don't exist yet. Richard Feynman understood this deeply. He saw what the education system was doing to children, and he fought against it. He showed us how to raise thinkers instead of memorization machines. Today, I'm going to show you what he discovered. I'm going to show you what's broken and how we're educating children. And I'm going to show you how to fix it, how to raise thinkers. Real thinkers. Children who can actually use their minds instead of just storing information in them. Hey, walk across stage. Let me start with a story. This story changed how Feynman thought about education forever. And once you hear it, it'll change how you think about it too. It's the 1950s. Feynman's father takes him for walks in the woods. Young Richard, maybe 6, 7 years old, and his father teaches him about nature, but not the way other parents teach. Not by telling him facts, not by making him memorize the names of birds and plants. Far share the method. Here's what Feynman's father does. They see a bird. And his father says, see that bird. Do you know what kind of bird that is? And young Richard says, no. And his father says, it's a brown-throated thrush. But in Germany they call it a Hausenfugel. And in Chinese they call it a chungling. And in Japanese a Katanotekta. Ice pause. No. His father says, you know what that bird is called in 4 different languages. But you still know absolutely nothing about the bird. You only know what different people call it. Continue the story. Then his father says, now let's look at what the bird actually does. See how it pecks at its feathers. Why do you think it does that? And they observe, they hypothesize, they think about it. Not memorizing names. Understanding behavior, thinking about why. Make the point, that's the difference. That's the entire difference between raising a thinker and creating a memorization machine. The memorization machine knows the bird is called a brown-throated thrush. That's what you're supposed to know for the test. That's what gets you the points. The thinker understands why the bird behaves the way it does, observes, questions, reasons, develops actual understanding of actual reality. A jumper get intensa, and here's what Feynman realized: most schools are teaching kids to memorize the names. This is a brown-throated thrush. This is mitochondria. This is the Pythagorean theorem. This is the capital of France. Names, labels, facts, information to be stored and retrieved. But they're not teaching kids to think about the bird, to understand mitochondria, to reason about why the Pythagorean theorem is true, to think about why Paris became France's capital. Or direct statement, they're creating memorization machines, not thinkers. And those memorization machines are completely unprepared for real life. Because real life doesn't ask you to recite facts. Real life presents you with novel problems that require actual thinking. Present the core issue. So let me show you exactly what's wrong. The specific ways our education system creates memorization machines instead of thinkers. Because once you see these, you can't unsee them. And you can start doing something different with your own children. And first problem. Problem 1, we reward correct answers instead of good thinking. A child solves a math problem, gets the right answer, gets a gold star, gets an A, gets praise. Another child solves a math problem, gets the wrong answer, but shows creative thinking, tries a novel approach, demonstrates genuine reasoning even though it doesn't work, gets an F, gets correction, gets disappointment. Pause. What does this teach children? It teaches them what matters is the correct answer. How you think doesn't matter. The process doesn't matter. Only the result matters, so facts make the impact clear. So children learn to find the shortest path to the correct answer. Memorize the procedure. Follow the steps. Don't think creatively. Don't try novel approaches. Don't risk being wrong. Just produce the correct answer. That's what gets rewarded. If Falzer share Feynman example of Feynman told a story about this. He's talking to a child who's been taught that energy is something that makes things go. So Feynman asks, does a coiled spring have energy? And the child confidently says no, because it's not moving. The child has memorized that energy makes things go. So if something isn't going, it doesn't have energy. That's the logic. Ayers make the point, the child got the answer wrong. But was the child stupid? No. The child was thinking logically from what they'd been taught. The problem wasn't the child. The problem was the teaching. Teaching a definition without teaching understanding. Teaching words without teaching concepts. Creating a memorization machine instead of a thinker. Second problem, problem 2, we punish mistakes instead of treating them as learning. A child doesn't know something, admits it, says I don't know, gets marked wrong, feels shame, learns not knowing is bad. A child tries to solve a problem, makes a mistake, gets it wrong, gets corrected, gets a bad grade, learns making mistakes is bad. I get passionate, this is devastating. This is how you kill thinking. Because thinking requires not knowing. Thinking requires making mistakes. Thinking requires being wrong on the path to being right. But we punish all of that. We punish admission of ignorance. We punish errors. We punish the entire thinking process. Let's make the contrast. Thinkers aren't afraid of being wrong. Thinkers expect to be wrong initially. That's how thinking works. You start with an idea, you test it, it's wrong, you adjust. You try again. You're wrong differently, you adjust again. Eventually you're right. But memorization machines are terrified of being wrong because they've been trained that wrong is bad. Wrong is failure. Wrong is shameful. Share what this creates. So they don't think, they wait to be told the right answer. They memorize it, they repeat it, safe. No risk of being wrong, no thinking required. Share Feynman's approach, or Feynman loved being wrong. When someone proved him wrong, he'd get excited. Oh, I was thinking about this incorrectly. Now I can think about it better. Thank you for showing me where my thinking was flawed. A being wrong meant learning, meant improving, meant thinking was happening. Actually make the point that that's a thinker. Someone who sees mistakes as progress, as information, as necessary steps toward understanding. But our education system teaches the opposite. Teaches kids to avoid being wrong at all costs. Teaches them to stop thinking and start memorizing. Third problem. Problem 3. We teach what to think instead of how to think. A child asks C, why is the sky blue? Most teachers say, because of Rayleigh scattering. The atmosphere scatters shorter wavelengths more than longer wavelengths. So blue light scatters more. The child memorizes this, repeats it on the test, gets an A. But does the child understand? Can the child reason about it? If you asked, why isn't the sky violet then? Could the child figure it out? No, because they memorized what to think. They weren't taught how to think about it. Acts show the alternative of Feynman's approach. Why do you think the sky is blue? What could cause that? Let's think about what we know. Light from the sun is white. So what could separate it into blue? What do we know about light and matter? What do we know about the atmosphere? Why the thinking? Don't provide the answer. Make the child reason. Make them think through possibilities. Make them develop the mental muscles of reasoning. Make the distinction. Teaching what to think creates memorization machines. They know the answer, but they can't think about similar questions. They can't apply the reasoning to new situations. They can't figure anything out they haven't been told. Teaching how to think creates thinkers. They might not know this specific answer initially, but they can figure it out. They can reason about it. They can apply their thinking to any question. Fourth problems. Problem 4. We test memorization instead of testing understanding. Tests ask, what is the capital of France? What is the formula for photosynthesis? Who signed the Declaration of Independence? Questions that have one right answer. Questions that test whether you memorize the information. Questions that a computer could answer better than any human. Pause, but tests don't ask, why did Paris become the capital instead of another city? Why does photosynthesis work the way it does? What were the different arguments about signing the Declaration? Questions that require thinking. Questions that test understanding. Questions that reveal whether you can actually reason. They make the impact. So students optimize for the test. They memorize facts. They don't develop understanding. Why would they? Understanding isn't measured. Understanding doesn't improve your grade. Memorization improves your grade. So that's what they do. That's what we've trained them to do. Share Feynman's experience. Feynman served on California's Curriculum Commission, evaluating science textbooks, and he was horrified by what he found. Books full of facts, full of definitions, full of things to memorize, but almost nothing that taught kids how to think scientifically, how to observe, how to hypothesize, how to test, how to reason. To share his reaction, he gave a scathing report. He said these books teach children science, without teaching them anything about how science actually works. They teach what scientists have discovered without teaching how to think like a scientist. They create memorization machines who can recite scientific facts but can't think scientifically. Fifth problems. Problem 5. We prioritize coverage over depth. The curriculum must cover 40 topics this year, so you spend 1 week on each. Skim the surface. Move on. Can't go deep. No time. Too much to cover. Make the impact so children learn a little about everything and understand nothing deeply. They skim surfaces. They memorize key terms. They move on before developing real understanding. They become memorization machines who know a little bit about a lot of things, but can't think deeply about anything. If I can make the contrast, thinkers learn deeply. They take one thing, they explore it thoroughly. They understand it from multiple angles. They connect it to other things. They develop genuine understanding that transfers to other domains. Better to understand 3 things deeply than to memorize facts about 30 things. Share Feynman's approach. Feynman would spend months on a single physics concept, exploring it, playing with it, understanding it from every angle, building intuitions, creating mental models. Other physicists would cover more material faster. But Feynman's deep understanding meant he could solve problems they couldn't, could see connections they missed, could think in ways they couldn't. Bars make the point. Depth creates thinkers. Breadth creates memorization machines. We're choosing breadth. We're creating machines. Pause. Bring it together. So those are the 5 problems. We reward answers instead of thinking. We punish mistakes instead of treating them as learning. We teach what to think instead of how to think. We test memorization instead of understanding. We prioritize coverage over depth. These create direct address, and together these create memorization machines. Children who can recite, who can follow procedures, who can pass tests, but who can't think, can't reason, can't solve novel problems, can't create. Get hopeful. So how do we fix this? How do we raise thinkers instead of memorization machines? Let me show you Feynman's principles. The specific things you can do, as a parent, as a teacher, as anyone who influences children to develop thinking instead of memorization. Principle 1, reward the thinking process, not just correct answers. When a child solves a problem, don't just check if the answer is right. Ask, how did you figure that out? What did you think about? What did you try? Reward good thinking even if the answer is wrong. Praise creative approaches. Praise clear reasoning. Praise willingness to try novel methods. Make it concrete. You got the wrong answer, but I love how you thought about this. You tried something I've never seen before. That's excellent thinking. Let's figure out together where it went sideways. Versus wrong. Here's the right way to do it. Memorize this procedure. Share the impact are the first creates a thinker. Someone who values good thinking and isn't afraid to try. Someone who learns from mistakes. The second creates a memorization machine. Someone who learns to follow procedures and never deviates. Haxa P, Principle 2. Make mistakes safe and valuable. When a child doesn't know something, celebrate it. Excellent, something you don't know yet. That means you get to learn something. Let's figure this out together. When a child makes a mistake, treat it as data. Interesting, you thought X, but it's actually Y. Why do you think you thought X? What made sense about that? What can we learn from this? In fact, make the mindset shift. Mistakes aren't failures. Mistakes are experiments that give you information. I don't know, isn't shameful. It's the starting point of learning. Create an environment where children aren't afraid to be wrong, where they're willing to try, where they learn from errors. Share Feynman example. Feynman's father did this constantly. Young Richard would have an idea about how something worked, and his father would say, "That's interesting. What made you think that? Let's test it and see." Not, "That's wrong." But let's think about this together. I say make the impact that created a thinker. Someone comfortable with not knowing, comfortable with being wrong, comfortable with the process of figuring things out. Principle 3. Ask questions instead of providing answers. When a child asks why, don't immediately give them the answer. Ask them, what do you think? Why do you think that happens? How could we figure that out? Make them think. Make them hypothesize. Make them reason. Guide their thinking. But don't do the thinking for them. Make it concrete to a child. Why do boats float? A bad response, because of buoyancy. Objects float when they displace water equal to their weight. Good response? Great question. Why do you think they float? What would make something float or sink? Let's think about this together. Share what this does. The bad response creates a memorization machine. The child memorizes buoyancy and displacement. Without understanding, the good response creates a thinker. The child reasons, observes, tests ideas, develops genuine understanding. Principle 4, focus on understanding, not coverage. Don't rush through topics. Go deep. Let children explore. Let them play with concepts. Let them understand thoroughly before moving on. Better to understand 3 things well than to memorize facts about 30 things. Make it practical. If your child is curious about how plants grow, don't give them a 5-minute lesson and move on. Spend a month on it. Plant seeds, observe daily. Experiment with different conditions. Draw pictures. Ask questions. Develop deep understanding. Share the payoff. That deep understanding of plants transfers. They learn about observation, about cause and effect, about patience, about experimentation, about systems. That's thinking. That transfers to everything. That's valuable. ACE Principle 5, teach through experience and discovery, not lecture and memorization. Don't tell children facts to memorize. Create experiences where they discover principles themselves. Hey, and make it concrete. Don't say things fall down because of gravity. Instead, drop different objects. Let them observe. Ask, what do you notice? What's the pattern? Why do you think that happens? Let them discover that things fall. Let them notice the pattern. Then introduce the word gravity as a name for what they've already discovered. If I share Feynman's philosophy, Feynman said, what I cannot create, I do not understand. If a child memorizes that gravity makes things fall, they don't understand gravity. But if they discover through experience that things fall, and then learn that we call this gravity, they understand. They created the understanding through experience. It's real, it's permanent, it's usable. Share transformation story. Let me tell you about a family who applied these principles. Call them the Johnsons. Their daughter, Emma, was struggling in school. Good grades, she could memorize and regurgitate. But she wasn't actually learning, wasn't developing as a thinker. They pulled her out of traditional school, started homeschooling using Feynman's principles. Share their approach and no textbooks, no curriculum to cover, no memorization. Instead, Emma got curious about something and they'd explore it deeply. She wondered how bridges work. They'd spend weeks on bridges, visit bridges, build model bridges, experiment with structures, understand the principles thoroughly. She wondered how music works, months on music, learning an instrument, understanding sound waves, composing, experimenting. Share what happened in the first year. She learned about maybe 6 topics, deeply, thoroughly, with genuine understanding. A traditional school would have covered 60 topics, superficially, through memorization. The result of 5 years later, Emma is back in traditional school, and she's the best student, not because she memorized more, but because she learned how to think. When given a problem she's never seen before, she doesn't panic. She thinks about it, reasons about it, figures it out, because she's a thinker, not a memorization machine. I can make the universal point that that's what happens when you prioritize thinking over memorization. You create someone capable, someone who can handle the unknown, someone who can actually use their mind. Address the concern. Now, some of you are thinking, but my child needs to pass tests, needs good grades, needs to get into college. I can't ignore the system. I can answer honestly, you're right. The system exists. The system rewards memorization. You can't completely ignore it. But offer the solution. But you can do both. You can help your child pass the tests while also developing their thinking. The tests require memorization. Fine, help them memorize enough to pass. But don't stop there. Don't make that the goal. Make thinking the goal. Make understanding the goal. The tests are just hoops to jump through. The real education is developing their mind. Make it concrete as your child has a biology test on photosynthesis. They need to memorize the formula. Help them do that. But also go deeper. Why does photosynthesis work this way? What would happen if it worked differently? How did plants evolve this? How does this connect to what we know about chemistry? Pass the test. But develop thinking. Don't let the test be the limit of learning. Share Feynman's own experience of Feynman did this. He passed tests. He got good grades. He succeeded in the traditional system, but his real education happened outside the tests. In exploration with his father, in figuring things out on his own, in thinking deeply beyond what was required. The tests were obstacles to overcome. The thinking was the actual education. There's present the bigger picture, here's the bigger truth. The world is changing rapidly. When today's children enter the workforce, most jobs will be different from what they are now. Many jobs will involve problems we can't even imagine yet. Situations that require adapting, thinking, creating solutions that don't exist. Make the stakes clearer, memorization machines will be obsolete. Computers already memorize better than humans. AI already retrieves information faster than any human can. But thinkers will be invaluable. People who can reason about novel situations, who can solve undefined problems, who can think creatively, who can adapt. A direct statement, that's what your children need. Not the ability to recite facts, the ability to think, and you can give that to them. You can raise thinkers instead of memorization machines. Present the practical summary. Here's how apply Feynman's 5 principles. 1. Reward thinking, not just answers. Praise the process. Value good reasoning even when it's wrong. 2. Make mistakes safe. Celebrate not knowing. Treat errors as learning opportunities. 3. Ask questions instead of providing answers. Guide thinking. Don't do the thinking for them. 4. Go deep instead of covering everything. Understand thoroughly. Don't rush. 5. I've learned through experience and discovery. Create, experiment, observe. Don't just memorize. Make the promise to do these things, and you'll raise a thinker. Someone who can actually use their mind. Someone prepared for a world we can't predict. Someone capable of handling whatever challenges emerge. Tell final story. Let me end with one more story about Feynman. Late in his life, someone asks him, "What made you such an exceptional physicist? What made you able to think in ways others couldn't?" And Feynman doesn't credit his intelligence. He credits his father, those walks in the woods, those questions, that approach to learning. Hot share his answer. My father taught me to think, not to memorize. He taught me to question, not to accept. He taught me to reason, not to recite. That's what made the difference. Not being smarter. Being a thinker instead of a memorization machine. Our final challenge, that's available to your children too. That kind of thinking, that kind of capability, that kind of preparation for the future. But only if you choose it. Only if you prioritize thinking over memorization. Only if you resist the pressure to create another memorization machine and instead commit to raising a thinker. The Zum walk to center. The world doesn't need more children who can recite facts. We have machines for that. The world needs children who can think, who can reason, who can solve new problems, who can create new solutions, who can adapt to unknown challenges. If I direct address here, your children can be those people. If you raise them as thinkers instead of training them as memorization machines. It's a final statement, so make the choice. Choose thinking over memorization. Choose understanding over coverage. Choose depth over breadth. Choose questions over answers. Choose reasoning over recitation. Raise thinkers. The world needs them. Your children deserve to become them. Thank you. And if you want to understand more about Feynman's approach to education, if you want more specific techniques for developing thinking instead of memorization in children, do me a favor. Like this video and subscribe to the Mind of Richard Feynman channel. We're exploring how to actually educate for understanding and capability, not just test scores. Join us. Let's raise thinkers together. See you in the next one.
Let's talk about electricity. You think you know what it is, don't you? I mean, you use it constantly. Right now, electrons are flowing through the device you're reading this on. Electricity is powering the lights around you, keeping your food cold, charging your devices. It's everywhere, so you must understand it, right? Okay, explain it to me. What happens when you plug something in? Where does the power actually come from? What is electricity at its core? Most people say something vague. It's energy, it's electrons moving, it's current in a wire. But here's what bothers me about those answers. They don't actually explain. They just rename the mystery. Sure, electrons are moving, but why? What's pushing them? And why does that pushing create light or heat or motion? The truth is darker than you think. The thing we call electricity is deeply, profoundly weird. And the way we teach it completely hides that weirdness. We make it sound normal, predictable, safe, but once you see what's really happening, once you peek behind the curtain, you realize that we're manipulating something absolutely extraordinary, something that breaks everything you think you know about how the world operates. Let me show you what I mean. Here's an experiment. Simple one. Take a piece of plastic wrap, rip off a strip. Now, rub it between your hands really fast like you're trying to warm them up. Now, hold it near the back of your hand without touching. Feel that the hairs on your arm are moving, standing up, reaching toward the plastic. You can actually feel the plastic pulling on you from a distance. Stop and think about that for a second. You rub plastic, that's it. No batteries, no wires, no power source, just friction. And now that plastic can reach across empty air and tug on your body. How? In your normal experience of the world, things only push or pull when they're touching. You push a chair, you touch it. You lift a book, you touch it. Forces require contact. Except here's a piece of plastic not touching you, pulling on your arm hairs through empty space. Most people shrug. Static electricity. We learned about that in middle school. It's not important. Not important. You're looking at the force that holds every atom in your body together, the force that makes chemistry possible, the force that allows your neurons to fire, your muscles to contract, your eyes to see. You're looking at one of the four fundamental forces of the universe, demonstrating its ability to act across distance. And you think it's a polar trick? This is the problem. We've become so familiar with electricity that we've how absolutely insane it is. Let's break down what just happened. When you rub that plastic, you scraped electrons off your hands and piled them onto the plastic. Just a few trillion extra electrons. And here's the thing, that's going to break your brain. Those excess electrons despise each other. They push away from each other with a force so large you literally cannot comprehend it. Let me try anyway. Take two electrons, place them 1 centimeter apart. The electromagnetic force between them is about 10 to the 42nd power times stronger than the gravitational force between them. 10 to 42, that's 1 followed by 42 zeros. The electromagnetic force is so incomprehensibly stronger than gravity that gravity might as well not exist. For electrons, gravity is irrelevant, meaningless. Electromagnetic forces are everything. So here's the question. If these forces are that monstrously strong, why isn't everything exploding? Why doesn't matter just tear itself apart? The answer is almost magical. Cancellation. Think about what an atom actually is. At the center, you've got protons with positive charge. Around that, you've got electrons with negative charge, positive and negative, plus and minus. And these charges follow one simple rule, like repels like opposites attract. The forces are exactly equal in magnitude. The push of repulsion equals the pull of attraction. So in normal matter, you get an intimate mixture of positive and negative charges. Protons and electrons packed as close together as physics allows. Every positive charge is surrounded by negatives. Every negative is surrounded by positives, and they balance out. The enormous repulsive forces are canceled by equally enormous attractive forces. Everything is neutral. The forces are still there. Those monstrous electromagnetic forces are still a seating, but they're balanced so precisely that the net effect is zero. And because the forces are so huge, even the tiniest imbalance creates effects. You can feel when you rub that plastic wrap, you move maybe 1 electron in every trillion. That's essentially nothing, but it's enough to make your arm hair stand up. Because when the underlying forces are that enormous, even the smallest excess creates a noticeable effect. This changes everything about how you think about matter. Pick up a mug, hold it in your hand. What are you feeling? You think you're feeling the solidity of ceramic physical substance. Wrong. You're feeling electromagnetic repulsion. The electrons in your hand are pushing away from the electrons in the mug with enormous force. The reason you can't push your hand through the mug is because the electromagnetic forces are so strong that the electrons refuse to overlap. Your hand never touches the mug. Not really. There's always a tiny gap between the atoms in your hand and the atoms in the mug. You're not feeling contact. You're feeling the electromagnetic force pushing back at you. And here's the thing that should completely restructure your worldview. All forces you've ever felt are electromagnetic. Every push, every pull, every sensation of touch or pressure or resistance, it's all electromagnetic repulsion and attraction acting at a distance. You have never touched anything in your entire life. Every time you think you're touching something, you're feeling Ingy. Electrons pushing away from electrons through empty space. The same force you saw with the plastic wrap just acting at smaller distances where the forces become enormous. Now let's talk about wires. You've got a copper wire stretching across your house. At one end there's an outlet. At the other end there's a lamp. You flip the switch. The lamp lights up instantly. What just happened? The standard explanation is that electricity flows like water. Electrons enter the wire at one end, travel down its length, and emerge at the other end. That explanation is completely wrong. Electrons in a wire move incredibly slowly, about 1 millimeter per second. At that speed, it would take nearly half an hour for an electron to travel across your house. But the lamp turns on instantly. So what's really happening? Here's the key. The wire is already full of electrons. Copper has lots of free electrons just sitting there ready to move. When you close the switch, you create a voltage difference. That voltage pushes on the electrons at one end of the wire, but because electrons repel each other across distances, that push immediately affects the next electron, which pushes the next one, which pushes the next one. It's like a line of people standing shoulder to shoulder. If you push the person at one end, the person at the other end feels it almost immediately, not because the first person walked down the line, but because the push was transmitted through the crowd. The push travels through the wire at nearly the speed of light. Not because individual electrons are moving fast, but because the electromagnetic force acts instantaneously across distance. That's what makes electricity useful. You can push here and something responds there almost instantly across huge distances. But where does the push come from? Let's trace it back. Your lamp connects to an outlet. The outlet connects to wires in your walls. Those connect to power lines, and those connect to a power plant. Maybe it's miles away, maybe 100 miles away. And at that power plant, something is spinning. A massive turbine weighing tons, rotating at thousands of RPM. And that spinning motion happening miles away is what's powering your lamp. How is that possible? The connection between that spinning turbine and your lamp is magnetism. Electricity and magnetism are the same thing. They're not two separate phenomena. They're two aspects of one unified force. The electromagnetic force, moving electric charges create magnetic fields. Changing magnetic fields create electric currents. They're inseparable. Here's how a generator works. You spin copper wire inside a magnetic field. The magnetic field pushes on the electrons in the copper. The electrons don't want to move, but the field is insistent. You force the electrons to flow. That's electric current. That's it. Motion plus magnets plus copper equals electricity. Now run it backwards. Push electricity through copper wire inside a magnetic field. The field P pushes on the moving electrons. The wire moves. That's a motor. Same phenomenon, just reverse. Generators turn motion into electricity. Motors turn electricity into motion. And the reason this works is because electricity and magnetism are unified. They're aspects of the same underlying force. This should seem impossible. You're telling me I can move metal in one place and other metal moves in another place with nothing physically connecting them except thin copper wire? Yes. You're telling me that spinning a magnet near copper generates a push that travels through wires and makes other copper move? Yes. And we use this every second of every day. Every motor, every generator, every power grid on Earth operates on this principle. Water falls on one side of a dam, turbines spin, copper moves through magnetic fields, electrons get pushed. Push travels through hundreds of miles of wire at nearly light speed. It reaches your house, makes electrons move through a motor. Your fan turns on. Water falling in one place makes a motor. Spin in another place, miles away, connected by nothing but thin metal wire. That's insane. You don't even need permanent magnets for this to work. Take a coil of copper wire, run electricity through it. The moving electrons create a magnetic field. Now move that coil near another coil of copper. The changing magnetic field pushes on electrons in the second coil. Current flows even though there's no physical connection. That's a transformer. That's how the power grid works. It's copper, just motion. That's all you need. Metal talking to metal across empty space using electromagnetic fields. Now, here's the thing that should completely change how you see reality. I said earlier that all the forces you feel are electromagnetic. All the pushing and pulling. All are touching and pressing. But think about what that means. The normal forces, the mechanical forces you experience every day, those aren't fundamental. Those are consequences of the electromagnetic force. The electromagnetic force is the fundamental reality. Everything else is derived from it. When you push on a door, you're creating electromagnetic repulsion between electrons in your hand and electrons in the door. When you walk on the floor, you're being held up by electromagnetic repulsion between electrons in your feet and electrons in the floor. When light hits your eyes, you're detecting oscillating electromagnetic fields causing electrons in your retina to move. It's all electromagnetic chemistry, electromagnetic forces, between electrons and different atoms, heat atoms vibrating because electromagnetic forces hold them in place. Biology, that's chemistry, which is electromagnetic, or your entire sensory experience of reality is electromagnetic interactions. And here's the deepest thing. You can't explain the electromagnetic force in terms of anything simpler. You can't say it's like a spring or it's like a rope, because springs and ropes are made of electromagnetic forces. The electromagnetic force is fundamental. It's one of the four basic forces of nature. You have to accept it as a brute fact about reality, and then everything else gets explained in terms of it. That's uncomfortable because the electromagnetic force acts at a distance, and that violates your intuitions. You've evolved to understand contact forces, but contact is an illusion. There is no contact. There's only electromagnetic forces acting across tiny distances. To understand electricity, to really understand it, you have to rebuild your intuition from the ground up. You have to accept that the universe is made of fields that permeate all of space, that charged particles push and pull on each other across those fields. That action at a distance is the rule, not the exception. When you flip a light switch, here's the real story. You close a circuit, electrons throughout the entire circuit start moving slowly about 1 millimeter per second. At the power plant, a turbine spins. Magnets rotate near copper coils. The changing magnetic field pushes electrons. Those electrons push on the next electrons. The push propagates at nearly light speed through hundreds of miles of wire. The push reaches your house. Electrons flow through the thin filament. The filament resists. It's hard for electrons to squeeze through. That resistance generates heat. The filament gets hot, enough to glow white. Electromagnetic waves radiate out. Some of those waves hit your eyes. The oscillating L. Electromagnetic fields cause electrons in your retina to move. Those moving electrons trigger chemical reactions. Signals travel through your neurons to your brain, and you see light. Every step is electromagnetic. The turbine spinning is electromagnetic forces. The signal traveling is electromagnetic repulsion. The resistance is electromagnetic forces. The light is electromagnetic waves. Your vision is electromagnetic. Think about how extraordinary this is. 200 years ago, none of this existed. Then we discovered these forces. We figured out how to manipulate them. We built machines that could generate electricity transmitted across vast distances and use it to do useful work. And in doing so, we completely transformed human civilization. Electricity gave us instant communication, telegraph, telephone, radio, television, internet, all electromagnetic. It gave us artificial light, cities that never sleep. It gave us motors, machines that can do work without human or animal muscle. It gave us computation, billions of tiny switches manipulating electromagnetic forces to process information. Everything, every single aspect of modern life runs on electricity. And it's all based on this one insight that there's a fundamental force that acts across distances. And if you learn to manipulate that force, you can do things that would seem like magic to anyone from 2 centuries ago. So what is electricity really? Electricity isn't a thing. It's not a substance or a fluid. Electricity is what we call it when we manipulate the electromagnetic force to do useful work. But more fundamentally, electricity is proof that the world is not what it seems. The world seems mechanical, solid, objects pushing against each other through direct contact. But that's an illusion. The real world is made of fields and forces acting at a distance, particles pushing and pulling on each other through empty space. When you see plastic or track paper, you're seeing the fundamental force that makes chemistry possible. When you turn on a light, you're commanding electromagnetic fields that permeate all of space. When you understand that, when you really understand what's happening, everything changes. You realize the world is electric, that forces act at a distance, that solid matter is just a carefully balanced dance of repulsion and attraction. And you realize that humans figured this out. We discovered these forces, we learned to manipulate them, we built a civilization on top of them. That's one of the greatest triumphs of human intelligence. So next time you flip a switch, remember you're not just turning on a light. You're manipulating fundamental forces. You're making electrons push each other across entire cities. You're converting motion to electromagnetic fields and back to motion. You're wielding power over nature itself.
On a routine flight between Helsinki and Tartu, a pilot glanced at his navigation instruments and felt a sudden cold wave of disbelief wash over him. The plane, which should have been coasting over the Baltic Sea, was inexplicably thousands of miles off course, hovering above a remote stretch of the Pacific Ocean on the opposite side of the world. Now this sounds like the opening to Lost. The reality is something much more scary. Russians, specifically a concerted body of activity to disrupt the way we navigate around our planet using the Global Navigation Satellite System, or GNSS, to provide GPS data. In fact, we can actually see this happening. This is the global survey activity that measures GPS threats and interference around the world. As we pan east, we notice a significant increase in the failure rate of GPS fidelity, with particularly high compromise exactly on the Helsinki-Tartu flight path. By assuming the line of sight is needed for this GPS attack, and looking at the signal strength in the area, internet sleuths narrowed down the likely source of this phenomena to just west of St. Petersburg. There's also another interesting dead zone, but that one's located in the USA just west of San Antonio. What initially got me interested in this story was videos like this one that had been circulating the internet for a while now and show in the middle of a drone show hundreds of drones suddenly falling out of the sky. There was an internet rabbit hole that I went down, that other drone companies were using GPS jammers to sabotage their competition. But all this brings me to one point in a world where our main means of navigation, both military and civilian, is so easily compromised. What do we do about it? I wanted to find out. So I reached out to a team of quantum physicists and engineers based in Oxford that are working on a solution, the world's first quantum positioning system that taps into the very nature of quantum mechanics in order to navigate. We hear a lot online, and you guys leave me a lot of comments that of quantum, much like fusion always seems 30 years away. This is a direct counterpoint to that argument. The magic behind their technique comes from the ability to control ultra-cold states of matter at inflection. We're experts in cooling and trapping atoms, and manipulating them using magnetic fields and light. And the reason that we do that is that if you cool down atoms exquisitely cold, few billionths of a degree above absolute zero, then you can create a new state of matter. It's called a Bose-Einstein condensate. What inflection are trying to do is develop a new approach to position sensing. But what exactly does that mean when we think about working out where we are on the planet? There are really two main ways of doing this. Either trilateration, which is used by GPS systems, where we have a constellation of GPS satellites in orbit, constantly sending out their position in the sky and the time on their local clocks. These radio signals travel outward at the speed of light from each satellite, and if you detect a GPS signal, you can look at your current time, subtract the time of the GPS signal, and this tells you how long it took for that GPS signal to arrive to you as all light. Waves move at the speed of light. The speed of light multiplied by this time difference tells you how far away the satellite is from you. You now know the distance, you just don't know the direction to this satellite. But if you can do this for 3 or more satellites, you can get a ring of overlapping possible positions that converges on a single point in the planet, telling you where you are. But actually GPS can be very easily spoofed and can be very easily jammed. So what I mean by jammed is it can happen for natural reasons. I'm in between large buildings, or I'm in a mountainous region, or maybe I'm under the ground, right? I'm on the tube. Trave. Ling around London, I'm not going to. Get a GPS signal. GPS can also be jammed with very cheap jammers that literally block the GPS signal. Spoofed is a little bit more insidious, where you look at your GPS signal. It tells you that you're in one place, you're really in another. That can be either in the theater of war, or like a few delivery drivers did a few years ago to disguise the fact they were taking naps throughout the day. If that is the case, then all of these break the reliability of GPS. If that goes down, you have to rely on something called dead reckoning, and dead reckoning is based on accelerometers, rotation sensors that measure inertial forces. Dead reckoning was originally developed by Sailors as early as the 1600s trying to navigate around the globe back then, all they had was a compass, and that gives you a direct direction, but not a position. So how do you work out where? Imagine you are a sailor trying to make your way over to America. You start by locating your position on the map by looking for the port you are leaving from. You decide to head to America by moving straight west. If we make the physicist assumption that ocean currents and stray winds don't knock us off course at all, and we follow our compass reading perfectly where we are on the map is a simple question of how long we've been traveling multiplied by our speed. Sailors determined a ship's speed by a log with a rope tied to it. Overboard every 47 ft a knot was tied in the rope, and by counting how many knots were pulled out by the log, the ship could determine how fast it was moving. This gave us the definition of speed, measured in knots still used by ships. And aircraft to this day, this worked. Okay, for sailors back then, but for some reason never caught on with commercial aircraft pilots, maybe because you need a lot more rope, but also because these systems weren't accurate enough, and velocity is rarely constant. So during the mid-20th century, particularly during World War II, dead reckoning systems moved to measuring acceleration rather than velocity. These worked broadly the same but measured acceleration over time. To calculate velocity, then velocity over time to calculate position. I like to think of this as basically what you do. If you ever find yourself kidnapped and put in the back of a trunk, you feel the movements of the car around you and keep track of your position. This process works because every action has an equal and opposite reaction. To understand this better, you might imagine Einstein in a rocket ship in space. As the rocket accelerates, he gets pushed to the bottom of the ship. Similarly, moving left or right causes him to bump into the opposite wall. The device that measures all of these movements is called an inertial measurement unit, or an IMU. It measures changes in acceleration or deceleration by watching its internal Einstein bump around. But why is this so interesting? It means that unlike GPS, no external reference signal is needed, which could otherwise be vulnerable to hacking, jamming, or poofing. Dead reckoning systems just need to know where they started, and they can use the laws of the universe to determine the rest. They are effectively unhackable, assuming at least that no one has direct access to the device. An elegant solution for keeping track of reality. The problem with normal IMUs is that their sensitivity is limited, and the reason for that is that all of these sensors have an unavoidable level of drift and noise, and that drift and noise accumulates over time. So you start off with your known position, and you integrate forwards your local acceleration and rotation for a few minutes, a few hours, and a few days, and eventually the uncertainty of your position grows and grows and grows until it's no longer usable. So imagine you're a submarine. You're trying to go from the middle of the ocean through a narrow straits Essachan gap without broadcasting your position. With sonar or any emissive technology, you then are more and more uncertain about your ability to navigate underwater. And I pick underwater because GPS does not penetrate underwater at all. So regardless of the situation, you always need inertial navigation. Underwater, the goal for inflection is to overcome the limitation of traditional inertial measurement systems by developing one based on the quantum properties of the universe and a state of matter called a Bose-Einstein condensate. Because I'm an experimental physicist and I like understanding how things actually work, I wanted to see deep within their system to see how the pieces of this puzzle come together. To do that, though, the first challenge is to make some of the coldest atoms in the universe. Can you start by just talking me through how you actually go about cooling an atom using a laser CU? That sounds utterly counterintuitive, you know. Like usually you think of lasers as heating things up. How do you actually use a laser to cool something down? So the basic concept is when the photon of light comes in and interacts with the atom, it sort of stays momentarily with the atom and then is re-emitted into the environment randomly in all directions. And because every time an atom experiences an interaction with the laser light, it loses a little bit of energy. Its kinetic energy is slowly sapped away as it interacts with many photons from the beams. And this happens in a way which opposes motion. So if the atom moves towards the laser beam, it scatters more light than if it's moving away from the laser beam. This Phenomena has been known for a while, but I always find it amazing. It's called Doppler cooling, as you might expect from the name. It exploits the Doppler effect, which is the change in frequency or wavelength of any wave perceived by an observer moving relative to the source. You're probably reasonably familiar with this in the example of a car moving towards you. As it moves towards you, its engine sounds like it's at a higher pitch or higher frequency than when it passes you and starts moving away. The same thing happens, though, with light. Atoms are exposed to a laser light that is slightly red-shifted, meaning that its frequency is slightly lower than the natural frequency that the atom wants to absorb. The atom's thermal motion is random in nature as it bumps into other nearby atoms, but when it moves towards the laser light, the Doppler effect causes the light to appear slightly blue, shifted, bringing the light's frequency closer to the atom's natural absorption frequency and making it easier for the atom to absorb the light upon absorbing. The photon, the atom experiences a recoil in the opposite direction to its motion, slightly reducing its speed after. Absorbing the photon, the atom will eventually reach the photon in a random direction. This process is repeated millions of times with the atom, absorbing photons from the laser light and losing a little bit more speed in each interaction. If lasers are applied from all 6 directions, this can slow down the atom essentially to a dead stop. Now that will slow the atoms down, but it won't trap them. So what we also add is a magnetic field, and that adds a restoring force, so the atoms are sucked into the center of the magnetic field. In this setup, we have 6 separate laser beams arranged, so one from this direction and its partner from above, one from this direction and its partner, and then one kind of in this direction and one traveling this way. And so this means that we have a laser beam in pushing the atoms in all 3 dimensions and both axes, and this is the first stage of what we will eventually do, which is to trap and cool atoms way colder than that, even to the state of matter, known as Bose-Einstein condensate. This magnetic optical trap, or MOT, means that you can hold on to these super cold atoms in the middle of a vacuum chamber like this and keep them away from the sidewalls of your container so they don't touch it and instantly start to heat up. This is kind of hard to see happening because, well, it's a cloud of atoms, but also the laser is in the infrared, which our eyes and our cameras aren't very good at detecting here. My eyes in our main camera couldn't see anything, but when I put my phone in front of our camera, you can suddenly see a bright red dot. This is the trapped cloud of atoms. That's because the DSLR that we're shooting on had an IR filter over the top of it, meaning that we couldn't see any infrared, but our mobile phones didn't. The team helped make this slightly easier to understand by blocking and unblocking the line of the laser, which you can see on this screen, with a special IR camera. The cloud of ultra-cold atoms spontaneously assembles and then kind of explodes as the trap and confinement is turned off. What's nice here is you can see as the atoms disappear, you can see them flying away because they're no longer held by the force of the trap, and they just expand ballistically into the volume of the vacuum chamber. And yes, this does look like a blurry smut on a screen, but that's quantum physics for you. It almost always looks like that. What was really impressive is how you can then make this atom cloud do something useful for you to understand how this system works. We need to get hands-on with the actual device. Cool, heavy, valuable input. Be this device, to say the least, is reasonably complicated. It's simple as long as you know quantum computing is quantum computing. What we're looking at here is what we call the double mop chamber. Generates a 2DM, so this is similar to a 3DM, but we're confined in 2 dimensions. It's a line cold atom. We deliberately leave the 3rd dimension free. That's so we can introduce what we call a push beam, so that's another laser beam along the axis, and that parts momentum onto the atoms in that axis, and they propagate up into the top chamber here. And so this is then where we do the 3-dimensional cooling, and then we can ramp those magnetic fields and the currents in the chip to load atoms into what we call the chip trap. Reason why we want to do that is because we want to generate this the coldest state. His is exactly what we want. We want to prepare Bose-Einstein condensate, and then we want to do atom interferometry with it in order to detect motion with exquisite precision. Interferometry looks at the interpattern between 2 traveling waves. It is used in experiments you might have heard of before, like LIGO, to detect gravitational waves as they move through the Earth. Usually interferometers interfere waves of light, but here we want to interfere. Waves of matter, this is kind of wild, I think we're all pretty familiar with. Light reflecting off of a material. Surface like a mirror, but it is. Reasonably rare that we see material reflecting off of a light surface, but that is exactly what is happening here. Here we can see the atoms from above. So the black wires here are how we're going to run current through there, and that's going to create. The trap, I'm going to shine a very powerful laser called a dipole laser. From the side, then I'm going to apply a coherent laser pulse, which will split this cloud into two. The atoms are going to move in opposite directions inside the dipole. Then we're going to coherently flip them back so that they recombine in the middle and after, completing this interferometry sequence. The phasor the atoms is sensitive to the acceleration, so we can take an image of the cloud and read out the portion of the cloud in each of the momentous state, and that will be a fingerprint of how the cloud was, accelerating during the measurement. That image is destructive, so we will no longer have a B Einstein condensate. The atoms will be warm and they'll be dispersed in the vacuum chamber, and therefore we have to start the whole cycle again, so we get one image every cycle, which is about once a second. So what this technique relies on is that if there are any small changes to acceleration, the ship moving up, down, left, right, forwards, or backwards, this will impart a small difference in the two clouds of atoms such that when they are brought back together and recombined, you see a small interference signal correlating to this acceleration. Don't get me wrong, every single step of this process is incredibly difficult, and it would be an impressive feat if it was demonstrated just in the laboratory alone, but this is already far closer to reality, and back in May the team flew this system on board a research flight to prove about its capability. This is a video that we took in flight. Here we are, you can see the aircraft banking, and on the screen you see a single blob there, and that blob is a Bose-Einstein condensate being produced in this particular video. We're alternating between taking a BC and then just imaging that directly and taking the BC and doing the first round of splitting. That you need to do for interferometry. Whether you split or whether you just look at the BC, you drop the atoms, they free fall briefly, and you do what's called absorption imaging, which is very simple. It's looking at the shadow. The atoms create, and by looking at the relative density of these three blobs, you know the relative proportion of atoms in each of the three superposition states, and then you can back calculate what phase you would have accumulated, obviously due to an acceleration or rotation. The fact that you can even brag, split a BC in a plane and it's stable is remarkable. It's really, really amazing. And you can do so while the aircraft moving around. You can see the cloud moving in the background to add some context as to why this is so impressive. The enemy of all quantum engineering is noise, both mechanical and electromagnetic. It's what we are fighting when we're building a quantum computer that makes it so hard to get, right? And what the team here is having to overcome, you come from a physics lab where everything is bolted onto FL floating optical tables, and the magnetic and the light environment and everything else is quite well shielded to taking this on a really dynamically challenging environment, like an aircraft where the aircraft is shaking violently because of the engines. There is a 6 gigs weather radar at the front of the thing blasting. There's air traffic control. It's a very challenging environment we are finally getting to, the point where quantum is becoming robust. The learnings that are here will map directly to other quantum technologies and open up applications that we never thought possible. The challenge now is to show the performance and the capabilities of the quantum senses in more of the deployed trials, and benchmark that against existing technologies and try to rapidly ascend that technology development curve. So lots of the existing technologies I mentioned before are plateauing in their performance. We're not going to get a 10x or 100x improvement in fiber optic gyros or ring laser gyros in the next few years. They've been very well engineered by lots of very smart people, but they're coming to the end of their development trajectory. We're just at the start of the development trajectory for quantum technologies. At the first generation of our products will be something that's rack-mounted system, something that can go into a data center or onto a ship or an aircraft, but ultimately where we're going longer term, and when I say longer term, this is over. The next few years is to ruggedize and miniaturize the systems using, for example, photonic integrated circuits. So taking the lasers and the optics and the vapor cells that you've seen and printing these on silicon so that ultimately these products will be something that could fit in the palm of your hand, but positioning isn't the only problem that these systems could tackle. So because the atoms are sensitive to acceleration, they are by the same exact principle sensitive to gravity. And so if we can measure gravity with exquisite precision, it enables us to, for example, understand where there are mineral deposits under the earth. We can measure tunnels, we can measure geologic formations. One day it may have applications from helping guide autonomous vehicles around high-rise cities or helping us to navigate space. But first it will be set to work to protect flights around the world, which, as of 2024, 900 flights a day on average, are now encountering GPS spoofing, technology made possible by some of the most complicated but fundamental laws of our universe. Diving into these sorts of technologies is literally the coolest thing about what it is that I get to do. As a factor of being on YouTube, if you like this video, I'm going to leave some more kind of behind-the-scenes footage over on Patreon and post it here for channel members. Please do consider supporting us by joining or just by leaving a like or leaving a comment. Let me know what other technologies you